In this video, we're continuing with our discussion of the chain rule and doing further examples. This is starting on page 4, example 5. So in example 5, we see we are given the function f of x equals 130 divided by 1 plus 12e to the negative 0.05x. This is a logistic function. We could use the quotient rule here, since I see it as one function divided by another, but in general, I tend to take a quotient like this and rewrite it. I'm going to take the entire denominator, think of the denominator as an expression in parentheses, and I'm going to flip it up to the numerator. Remember, if you're dividing by an expression, that's the same as multiplying by that expression raised to the negative 1. So f of x can be written as 130 times that expression in the denominator in parentheses, all raised to the negative 1. When I write the expression this way, when I write the function f of x this way, I can see that there is this inner function here, 1 plus 12e to the negative 0.05x. So that inner function is our t of x function. So wherever I see t, I can replace it with t, variable. So now I can see that f of x can be viewed as this outer function, 130 times t to the negative 1, where t is the function 1 plus 12e to the negative 0.05x. All right, so we have our inner function and our outer function. Now we want to go ahead and find the derivative of the outer function and the derivative of the inner function. So the df dt, the derivative of the outer function, would be negative 130 t to the negative 2, and then replacing t with t equals 1 plus 12e to the negative 0.05x, we see we have negative 130 times 1 plus 12e to the negative 0.05x raised to the negative 2. So there's negative 130 t to the negative 2. That's the derivative of the outer function. And then we need to also find the derivative of the inner function. The derivative of 1 is 0, and the derivative of 12e to the negative 0.05x is 12e to the negative 0.05x. But remember, you have to multiply by the derivative of that exponent. So we have to multiply by negative 0.05. Again, there's a little hidden chain rule there. A lot of students miss that. Don't forget to multiply by the derivative of that inner function. So you're going to have to multiply by negative 0.05. So putting it all together, we need to find the derivative of f of x, which is df dx, or f prime of x. It's the derivative of the outer function times the derivative of the inner function. Let's try example 6. In example 6, we have the function 275 times 1.04 raised to the x squared. Observe here that it looks a lot like an exponential function, except instead of it raising it to the x power, we raise it to the x squared. So that is the inner function. T of x equals x squared. So we can view this function as looking like 275 times 1.04 raised to the t, where t is the function x squared. So now we can find the derivative of the outer function. The derivative of 275 times 1.04 to the t is 275 times 1.04 to the t times natural log of 1.04. And remember, we always need to replace t with the expression for t. So that's 275 1.04 to the x squared times ln 1.04. And we have to find the derivative of the inner function. That's not true. There's no hidden chain here. The derivative of the inner function is just 2x. So we have the derivative of the outer, and we have the derivative of the inner. So overall, df dx, we have to multiply the derivative of the outer function times the derivative of the inner function. In example 7, we're told that a balloon begins with a radius of 4 inches, and then the radius decreases by 0.05 inches per second. So that means that we have a linear function for the radius. It outputs radius when you input t, which is the number of seconds that have passed. So it starts at a radius of 4, and then it decreases 0.5 inches per second times the number of seconds. So there's our radius function. And if the balloon were perfectly spherical, then the volume of a sphere is 4/3 pi r cubed. So you can plug in r equals the radius of the spherical balloon, and it outputs the volume inside that balloon. Now we have this function v of r, and we have this other function r of t. It seems natural that we could find a formula for v of t, where you plug in the number of seconds and it spits out the volume of the balloon. So notice that would be, instead of taking v of r, you could plug in the function r to v. So instead of v of r, you plug in the function r. So you're finding a composition function. We start with the volume function, 4/3 pi r cubed, but instead of plugging in the number r, we're going to plug in the function r. Notice what we now have is a function for volume where you plug in the seconds, t equals seconds, and it spits out the volume of the balloon. Kind of skips over that intermediate step of first finding the radius. So we have a formula here for volume, and it asks us to find the derivative of volume, dv dt. Notice here that we definitely have a chain rule sort of problem. 4/3 pi times a function cubed. So if we need to, we can go off to the side and we can think outer function and inner function. Our inner function is this 4 minus 5t, and its derivative of the inner function is just negative 0.5. We have an outer function, which is like 4/3 pi times big capital T cubed, and the derivative of the outer function would be 4/3 pi is sitting out front. It's just a number, a constant out front. And the derivative of t cubed is 3 times the t squared, but the t is this inner function. So the outer function's derivative would be 4/3 pi times 3 times, instead of capital T, it's the entire function, 4 minus 0.5 t squared. So here's the derivative of the outer, here's the derivative of the inner, and the derivative of the volume function overall would be 4/3 pi times 3 times 4 minus 0.5 t all squared. There's the derivative of the outer times the derivative of the inner function, which is negative 0.5. We can do a little simplifying here. 3 in the denominator cancels with 3 in the numerator. 4 times negative 0.5 will just give us negative 2. So I'm going to write negative 2, and then there's pi, and then 4 minus 0.5 t squared. So there's dv dt. Derivative of volume with respect to time. And it asks us to go ahead and plug in t equals 1 and interpret. I popped these into my calculator. I plugged t equals 1 into the v of t function, and I found that it outputs 179.59. And I plugged t equals 1 into our derivative function, and I found that it outputs negative 77. So we're saying at 1 second, the balloon has a volume of 179.59 cubic inches. Furthermore, at that time, at 1 second, if you go 1 more second, the balloon's volume will decrease by 77 cubic inches.